Binomial expansions. You know the formula, you think you're set, but then the next thing you know, the examiner hits you with these three curveballs. And that's especially irritating if you thought you were set on this topic, but then you missed out on the minor nuances that ended up costing you a lot of marks. So here are the three areas where examiners try to trip you up when you're doing binomial expansions in Edexcel. Right, so area 1. This is where the exam gives you a fraction, and before you can even think about binomial expansion, you need to split it into partial fractions first. So the question will usually say something like, quote, express in partial fractions and hence find the binomial expansion up to the term x cubed. The key word there is hence, okay, because it means you have to do the partial fraction bit first and then expand it. So let's get into an example, a hard type of example of how they're going to try to trip you up here. Alright guys, so for our first example here, what we have is 2 plus 7x, okay, over 1 minus x times 1 plus 2x squared, okay. And it tells us to express this in partial fractions. And we're also told to find the binomial expansion up to and including the term x cubed, okay. And then obviously state the values of x for which it is valid. Now, as you can see, this is a classic scenario where we are mixing two areas, seemingly unrelated areas together, okay? And this is something that can trip people up. So, first thing I'm going to do is say, look, 2 plus 7x over 1 minus x, 1 plus 2x squared. What does that actually equal? What that equals is a over 1 minus x plus b, okay, that's going to be over 1 plus 2x. And we're going to have c, okay, over 1 plus 2x squared. Now why do we have that? We have that because this here is a repeated factor. Okay, we have to repeat it because it's squared. And again, that's just demonstrating that these minor things from other topics can come to bite you if you don't understand them properly. Okay, so we got that here. So next thing I'm going to say is, okay, look, 2 plus 7x then, that's going to equal a times 1 plus 2x squared, okay, and then times by b, 1 minus x, okay, then 1 plus 2x, okay, and lastly c, what's that going to be? Well, it's going to be times by 1 minus x. So after this, guys, we can now say, well, how are we going to get to a situation where we can solve for a, b, and c? Well, what we need to do from here is, first things first, I'm going to let x equal 1. Why am I going to let x equal 1? Because if we let x equal 1, the c here is going to cancel, and also the b. So then we can find something for a. Okay. So therefore we have 2 plus 7 times 1 is equal to a 1 plus 2, 1 squared, okay? So therefore we have 9, okay, which equals 9a. What does that mean? Well, a is obviously going to equal 1 then, right? Perfect. And the next thing here is we can do the same for 1 plus 2x, okay, because what does 1 plus 2x need to be? So what does x need to be for 1 plus 2x to equal 0? X needs to equal negative half there, okay? So I'm going to say let x equal negative half. Okay, so therefore we have 2 plus 7 negative half. Okay, that's obviously going to equal 0 plus 0 plus c. Okay, and that's going to be times 1 minus a half. Okay, which means what? Well, that means that negative 3 over 2, okay, that's going to equal 3 over 2 times c, which means that c therefore is going to equal -1. Okay, so what we have here, guys, is a equals 1, c equals a -1. Now what about b? What do we do for b in this scenario? Well, for b, what we're going to do here is say, look, we know that 2 plus 7x, okay, is equal to this plus this plus this, okay? So really what we have is 2 plus 7x plus 0x squared, okay? What does that equal? That equals a 1 plus 2x squared plus b 1 minus x 1 plus 2x plus c 1 minus x. Okay, so as a result, guys, what that means here is that, listen, we can equate the coefficients, and once we equate the coefficients, we can find a value here for 4b. Okay, and the easiest one here to do, I'd say, would be the x squared coefficient. Okay, because we know a and we know c, so if we do the x squared, we can form quite a simple equation. So we can say that 0x squared, okay, and the x squared coefficient in this binomial is going to equal what? That's going to equal 4x squared. Okay, so therefore we're going to have 4a x squared there, okay, because we're expanding this out. Then we're going to have b times what? Well, b, the coefficient here is going to be -2, okay? So we're actually going to have -2b squared -2b squared here. Okay, meanwhile c evidently does not have a x squared. Okay, there's no x squared coefficient here. So therefore what we're going to say is, listen, we can cancel these coefficients. I can say that 0 is equal to 4a minus 2b. Okay, we know what a is. What's a? Well, a equals 1, right? So I'm simply going to say 4 minus 2b. So therefore 2b equals 4, b equals 2. Okay, so perfect, guys. We've got our coefficients, sorry, we've got our constants b, c, and a. As a result, that means that 2 plus 7x, okay, it's going to equal 1 minus x, 1 plus 2x squared, okay, which is going to give us 1 minus x, okay, for a. Then for b, we've got 2, that's going to be 1 plus 2x. Okay, now for c, remember that was a minus, so I'm going to say minus 1 over 1 plus 2x squared. Okay, perfect. So as you can see here, we haven't even got to the expansions yet, but this question has taken quite a lot of setting up, and without the partial fractions element, this would have been likely impossible, or very challenging. Okay, so from here, guys, we're going to say that this is going to equal 1 minus x to the -1 plus 2, 1 plus 2x to the -1, minus 1 plus 2x to the power of -2. Okay, and now it's a case of simply saying, well, look, we've got our polynomials here, our binomial expansions. We're just going to expand them out. Okay, so when we do that, I'm going to skip past this because it's quite boring, but applying the formula, we get the following. Alright, guys, so evidently, as you can see, what we have here is the expansions for all three of these terms. Okay, and the key thing here is, again, remember what the question wanted. They wanted it up to and including the term x cubed. Okay, so now we've got to kind of combine these together. So x cubed here, up to x cubed, what are we going to say? Well, okay, the constants, we got 1, we got plus 2, and we got minus 1. Okay, so that means we're going to have 2. For the x term, we have 1x, we have minus 4x, we have plus 4x. So therefore we're just going to plus x. For the x squared term, we have 1x squared plus 8x squared minus 12x squared. Okay, so therefore minus 3. For x cubed, we have 1x cubed minus 16x cubed plus 32x cubed, which means we have plus 17 x cubed here. Okay, so that is going to be our expansion up to x cubed. Okay, but wait, we're not done yet, guys, because look, it wants us to state the range of values for x, okay, for which the expansion is valid. Okay, so what do we do now? We have 3 expansions. How does this all tie in together? Well, the trick here is to say, okay, so for validity, okay, we know it must be valid for all 3 expansions. Okay, so our validity inequality must be valid for all 3 expansions. Okay, so what does that mean? So expansion 1, so for 1 minus x to the minus 1, that must be valid for the absolute value of 1 being smaller than 1. Okay, because again, we can't have x equaling 0 here, because when it equals 0, that's when we get a undefined number, right? So that's important. Okay, so 1 minus x to the power negative 1, that's valid for the absolute value of x being smaller than 1. Okay, next for 1 plus 2x, okay, that's going to be valid so long as x, the absolute value of x, is smaller than a half. Okay, why? Because again, we equate this to 0. That tells us that we know that 1 plus 2x, sorry, must be smaller than 0. We equate it, we get the absolute value here, right? And the same thing for the other one. Okay, so as a result, as the absolute value of x is more than a half, okay, is our kind of base case here, okay, we can therefore say that, look, so the overall validity, what's that going to be? The absolute value of x is going to have to be smaller than a half, okay? So that's going to be the final answer to that question. Alright guys, so as you can tell, this is quite a long and extensive question. But the key principle here is they're combining both. And what you really need to know is, in this case, it was all about the partial fractions. That was really the bottleneck. And what was that bottleneck? It's the fact that 1 plus 2x is a repeated factor, okay? So this is where the examiner is really trying to combine things together. And this is often how these questions get people. So it's important to brush up on partial fractions because 1 plus 2x squared was a repeated factor which meant we needed b over 1 plus 2x plus c over 1 plus 2x squared. Okay, and obviously the a before as well. But that's the key thing here. So the bottleneck was the partial fractions. So if you didn't understand the partial fractions aspect, there might have been a bit of difficulty here. Alright guys, so you've got the partial fractions bit set up. That's all good. But now what if the examiner, instead of giving you a generic expansion like 1 plus x to the power negative half, we now have something like 4 plus 3x to the power negative half. How does that 4 there, instead of just a generic 1, change things up? Alright guys, so here we have an example of a compound binomial expansion. So, whereas before, okay, we might have had something like 1 plus x to the power negative 1, now, okay, in this instance we've got an 8 here, okay, and you simply cannot expand with that 8 there. So what do we do in these situations? Well, in a situation like this, we're simply going to say the following. 8 plus 6x, okay, to the power of minus a third, that's going to equal 8 power minus a third, okay, and then 1, actually, before I even do that, that's going to equal 8, 1 plus, and then if we divide 6x by 8, what do we get? We're going to get 3x over 4, okay? And let's put that all in the one bracket here. Raise it to the power of a third. What does that mean? Well, therefore, what we get is 8 to the power negative a third times 1 plus 3x over 4 to the power negative a third. Okay? Fantastic. So now, what we have here is a constant, and meanwhile over here, we have a very clear expansion that can occur because we've got the 1 here. Okay? So if we do that now, we simply get a half, okay? And we get 1 plus 3x over 4 to the power negative a third, which is great. But now the question becomes, well, how do we expand this? How do we do that? Well, I can say that 1 plus 3x over 4 to the power of negative a third. Okay, if we expand that using our traditional formula here, we're going to get 1 minus x to the power of 4, okay, plus x squared over 8, okay, minus 7x cubed over 96, okay, but we're not done yet. Why? What have we missed out on? Well, remember, this was all multiplied by a half in the beginning. So I'm going to do times a half here. Okay, which means that a half, 1 plus 3x over 4 to the power negative a third, is going to equal, okay, half minus x over 8, okay, plus x squared over 16, okay, minus 7 x cubed over 192. Okay, so evidently, you know, this wasn't the hardest question in the world, but it illustrates a key point. Okay, and that key point is basically that whenever you have a number here that is not 1, okay, we now have the number 1 here, we've got an issue. We need to solve that because otherwise our expansion formula just simply won't work. So the key thing, take it out. Okay, we've got it all under the umbrella of our exponent here. Multiply it. Okay, using our exponent rules. Or let's say multiply. Obviously, just use exponent rules to put it in. Okay, and when we expand it all together, we get this. But we're not done here, guys. Why? Because our next point here is validity. We need to see what values of x are valid. Okay. Now the key thing here is that we're going to say, okay, well, we know that 3x minus 4 3x minus 4 must be smaller than 1. Okay, in order for this to be true here. Okay, or to be even more precise, the 3 times the absolute value of x. Okay, so as a result, what does that mean? We have 3 times the absolute value of x being smaller than 4. Therefore, the absolute value of x, okay, our magnitude, that is, must be smaller than 4 over 3. Okay, so that is how we're going to do our validity. So again, not too difficult, guys, to be honest. But the key thing here is simply knowing, taking out our non-1 constant in the beginning, because we need to get it in this form for it to work. Alright, so you know how to do partial fractions when it comes to binomial expansions, and you know how to do the compound binomial expansions, but now sometimes the examiner slips in a little hence find the approximation question, and that usually comes right off the back of one of these expansion questions. Usually this can be free and easy marks if you know what you're doing, but oftentimes you can still run into little mistakes here that leave those marks in the table. Okay, so let's get into an example and I'll show you exactly what I mean. Alright guys, so jumping into an example here, okay, it says that by choosing a suitable value of x, use your expansion to find an approximation for 1 of the cube roots of 9.2, okay, to 5 decimal places. So what this is an extension from our previous expansion. So how do we go about doing this now? Well, the first thing I'm going to recognize, and this is, again, when I say leaving marks on the table, you'll see this is actually easier than expected, but it's these minor things that can add up, right? So that's why it's important to know. So 9.2 to the power of negative a third, okay? That's what we've got over here. Okay, but we also have 8 plus 6x to the minus a third, okay? So therefore, 8 plus 6x, we can equate that now to 9.2. Brilliant. And that means as a result that 6x is going to equal 1.2. Okay, so we have x equaling 0.2 here. Fantastic. So x equals 0.2. Brilliant. Now, we're going to say, firstly, for validity, .2, absolute value, the magnitude of it, smaller than 4 over 3. Okay, so we're set. Okay, that's that slight important point there. And from here we can say that, okay, listen, 1 of a cube root 9.2 is therefore going to equal the expansion, except this time we're plugging in x equals 0.2. Okay, so we're going to have a half, okay, minus 0.2 over 8 plus 0.2 squared over 16 minus 7 0.2 cubed over 192. Okay, and when we simplify that, guys, what that becomes is 0.5 minus 0.025 0.0025 minus 7 over 24,000. Okay, no point putting this in decimal format. Okay, and when we sum that all together, what we're going to get is 0.47721. Okay, and that's the 5 decimal places here. So the key thing here, as you can see, is it's not too difficult, but there are some slight minor points you need in order to ensure that you actually get it properly right. Okay, perfect. Now we've got our answer, but now what are the key mistakes that people sometimes make that would have made this completely impossible from the get-go? Well, the first thing here is substituting, in this example, x equals 9.2, okay, instead of 0.2. And the reason for that is because, remember, our expansion is 8 plus 6x to the power of negative a third, not x to the power of negative a third. Okay, so therefore we need 8 plus 6x equals 9.2, not x equals 9.2. That's the key thing there. Okay, you need to substitute the right value in. And the second thing is not checking the validity range. This is important because, remember, we have a validity range as to what value is actually valid, okay, for x. So in this scenario, we've got 0.2, okay, and that's perfect because that's obviously smaller than 4/3. However, getting another value that wouldn't have fit this range, then we would have run into an issue. Okay, so it's always important to make sure you're substituting the right value for x and also checking the validity range.